Good evening, my name is Janne, and this is my project Skin Cancer Classification using Small Data Sets. This is my larger and in-depth video where I'll talk about all the different parts that I compiled to make this project. So an introduction is that skin cancer is the most common type of cancer around the world, and it's very treatable in the early stages. However, if you let the skin cancer progress, if it's undetected at an early stage and metastasizes to other parts of the body, then this becomes very harmful because it's much easier to remove a malignant tumor that's skin deep rather than something that has spread throughout the bloodstream, the bone marrow, or the lungs. So good data is very important for classifying skin cancer and any other type of medical technology. So what I found was the HAM 10,000 dataset, which was compiled by Harvard, and it classifies 7 different skin lesions into various different disease categories. The 4 I've labeled out here are malignant or questionable, and some of these, for example, are basal cell carcinoma and melanoma, and some of the more benign cases, which are specific skin diseases that sometimes tend to look like skin cancer, though are not life-threatening. So image augmentation was a big part of this project. Because only 10,000 images were present, I wanted to make the dataset larger so that training accuracy and validation accuracy were higher, that we weren't overfitting to the specific data. However, there is a rule present when visually detecting skin cancer called the ABCDs. And basically, asymmetry, border irregularity, color, and diameter are the main factors that determine if a tumor or a mole is likely cancerous. So I needed to make sure that my image augmentation methods were not manipulating this in a way that was harmful to the diagnosis. And as you can see, I generated some images using parameters that I fine-tuned, and I'll mention later, that does not harm the image. The network architecture that I used was the Inception model created by Google for the ImageNet challenge. I didn't have the computational power to train the whole model from start, so instead I imported the ImageNet weights and trained on the last 2 inception blocks. This actually might not be such a bad idea anyways, even if I did have the computational power, because keeping the first part stagnant maintains the activations for things like edges and corners and, for example, edges of a disc, which is what most of the lesions look like. So this ended up working fairly well. As you can see, here's the first diagram of the full inception set, and here's the part that I'm specifically training. And these are 2 inception modules, which I'll talk about next. So each inception module is the premise behind the inception module is that there's valuable information at every pooling or dropout layer, and that information can be taken from 1x1s, 3x3s, and 5x5s. But traditionally, convolutional networks have only done one type of filter at each stage. The inception model uses all 3 and concatenates them. So at every inception module step, you're increasing the depth artificially. However, you're increasing the information that's passed on to the next layer. And in turn, this is believed to pass on more valuable information for classification. If you want to code this yourself, Google has their own Code Labs example that shows you how to do transfer learning with the inception model, or you can import and incorporate your own inception module, which I've displayed here through Keras, which is very trivial. There's also different medium blogs examples, and I mentioned one of the medium blogs over here, which talks more about this type of technology. So the first step to implementation is importing all the proper data. The way we have to do this is that the diagnoses for these images are in a separate CSV file, so we have to pair these manually to the correct images, and we do this through the name of the image, which is the ISIC code. And as you can see, once we've done this, melanocytic nevi is paired with this image and this image name. We also have to shuffle the data because this data is sorted by diagnoses, so all the melanocytic nevi are next to each other, all the melanomas are next to each other. So we have to separate this out so our training set is diverse enough to give us good predictions. Then we have to incorporate one-hot encoding. I just did this alphabetically, and as you can see, these are the different types of categories that the HAM 10,000 gives us, such as benign keratosis-like lesions, dermatofibroma, vascular lesions, and then down here you see more of the malignant cases, such as basal cell carcinoma, actinic keratosis, and melanistic nevi. Next, here's where I'm talking about the image augmentation part. As you can see, the coefficients of change are very low for things like width shift range and height shift range. You'll also note that I completely removed zoom because the diameter of the lesion was one of the rules for the ABCD rule list. You'll note that these coefficients are very small compared to the assignment we did, where we used about 0.6 or 0.7 for the cats and dogs. And also, uniquely about the lesions is that the rotation range can actually go a lot higher because there's no true north for a lesion. However, for a cat and a dog, there is a true north. Crafting the model is pretty simple. You can import it straight through Keras with the weights already installed. Then I added 2 dense layers. One was 128 neurons and one was 7 neurons. And this was activated by softmax to represent the 7 classes. To train the last 2 inception blocks only, it's every layer after 249 because there's a lot of layers in this model due to the concatenation. But as we stated before, this is actually a net positive. Training is fairly simple. I'm using stochastic gradient descent, which is recommended actually in the academic paper that Google wrote when they published the first inception model, with momentum and a small learning rate. And this small learning rate is specifically due to transfer learning because you don't want to mess up the parameters too much that already worked really well for ImageNet. I'm using categorical cross entropy, and I'm metricing on accuracy. So here are some of the results. On the validation accuracy, I'm getting about 69% plus or minus 0.09%. And for binary test accuracy, which I was really proud of, I got about 87% binary test accuracy. That's to say that about 87% of the time, the network at least correctly diagnoses if the lesion is malignant or benign. And this means something because this shows that at the very least, it can give you a much greater than chance prediction that there is a problem medically or not. Finally, here's my confusion matrix. This is normalized, but basically what it shows is it shows the sensitivities of the model and where the model is over-predicting or under-predicting. On one axis, you'll see a true positive. On one axis, you'll see a predicted positive. Ideally, what we would like to see is a diagonal line straight through the middle, and all those are white. However, we don't see that. However, the good news is that the false positives are occurring in the cancerous regions, such as melanomas and melanocytic nevis. This is good because at the very least, we're predicting or we're overdiagnosing rather than underdiagnosing. And this in turn means that we're not leaving cancers undetected, at the very least. So taking a little more look at my demonstration, taking a little greater look at my demonstration, you can see that the model summary is very long for this, and that is represented by the long inceptions that we have going on. And as you can see, the depth is getting very, very long. However, as we can see towards the end of this, we only have actually about 11 million trainable parameters. When you compare this to something like ResNet or DenseNet, they have 40 or 50 million parameters, or VGGNet. They have tens of millions of more parameters. So this was Inception Network was actually specifically designed for a low computational space. Further down, you can see I did some of my predictions here, where this is where the 69% comes from. And finally, after I generated my confusion matrix, I wanted to see if training was all that better. So I ran it overnight for about 200 more epochs to see if there was anything different. And as you can see, after 112 epochs, we're really not pushing that much on the validation accuracy, which suggests that maybe some other parameters might be changed. Or potentially what we could see happening is 2 inception blocks can only get you so far for the validation accuracy. That if we wanted to do a better, if we wanted to get better results, maybe we could do 3 inception blocks or 4 inception blocks and keep only the first 2 as frozen layers. Where I see this technology going in the future is deployment to mobile applications. I think this is a really strong technology for something like that. It would be very helpful for areas that don't have easy accessibility to medical care, or areas where there might be ignorance about medical care, where people are not inclined to check their lesions frequently and their moles. They are not worried about them being an issue. That's about it for my project. I hope you